Welcome to a lesson on how to determine the least squares solutions to the equation matrix A times vector x equals vector b. Let's suppose that matrix A times vector x equals vector b has no solution. We can compute an approximate solution by determining the least squares solution. Looking at the theorem below, if we let A be an m by n matrix and let vector b be a vector in Rm, a least squares solution of matrix A times vector x equals vector b are the solutions to A transpose times A times vector x equals A transpose times vector b. So notice how we simply multiplied both sides of the equation by A transpose. So to compute a least square solution, step 1, we compute A transpose times A and A transpose times vector b. Step 2, we form an augmented matrix for the equation A transpose A times vector x equals A transpose times vector b, and write the augmented matrix in reduced row echelon form. Step 3, the solution is a least squares solution. Let's look at an example. Let's find the least squares solutions to matrix A times vector x equals vector b, where matrix A is the given 3 by 2 matrix and vector b is the vector 6, 0, 0. Let's first verify there is no solution to the equation A times vector x equals vector b, where the corresponding matrix equation would be the equation shown here on the right. To try to solve this, we would write the augmented matrix, where the first row is 0, 6, 1, the second row is 1, 1, 0, and the third row is 2, 1, 0, which we see here. I've already written this in reduced row echelon form. Remember, the first column would be the coefficients of x1, the second column would be the coefficients of x2, the third column would be the constants. Notice we have a contradiction in row 3. The third row indicates that 0 equals 1, which of course is not true, which verifies the equation A times vector x equals vector b has no solution. So now to find the least square solution, we need to find A transpose times A as well as A transpose times vector b. Remember, to find A transpose, we take the first column of matrix A, and this becomes the first row of A transpose, and the second column of matrix A becomes the second row of A transpose. So now we need to find A transpose times A, which I've already done here. The result is the 2 by 2 matrix, where the first row is 5, 3, the second row is 3, 3. You may want to pause and verify this product. Next, we find A transpose times vector b, which again I've already done here. The result is the vector written as a column matrix with entries 0, 6. So now that we have A transpose times A as well as A transpose times vector b, step 2 is to set up and solve the equation A transpose times A times vector x equals A transpose times vector b, which gives us the following matrix equation. Next, we write the corresponding augmented matrix and write the augmented matrix in reduced row echelon form. So for the augmented matrix, the first row is 5, 3, 0, the second row is 3, 3, 6. With the augmented matrix in reduced row echelon form, notice x1 equals -3, x2 equals 5, and therefore the least square solution is the vector -3, 5. Instead of using vector x for the least square solution, we often use different notation. In this case, I'm going to use the vector x hat. So the least square solution is x hat equals the vector -3, 5. Remember, this solution minimizes the distance from matrix A times the vector x hat to vector b. Going back to the original problem for a moment, if there was a solution to the equation matrix A times vector x equals vector b, there would have been a vector x1, x2, where matrix A times the vector x1, x2 is equal to the vector 6, 0, 0. Because there was no solution, we found the least square solution, which gave us the approximate solution of vector x hat equals the vector -3, 5. Notice matrix A times the vector x hat is equal to the vector 5, 2, 1, not the vector 6, 0, 0. So the next question might be, how close is the vector 5, 2, 1 to the vector 6, 0, 0? We can determine this by determining the magnitude of the difference of vector b and the vector resulting from matrix A times vector x hat, which is the vector 5, 2, 1, which gives us the magnitude of the difference of the vector 6, 0, 0 and the vector 5, 2, 1, which results in the square root of 6. This indicates that the vector 5, 2, 1 is square root 6 units from the vector 6, 0, 0. Let's take a look at this graphically. First, the purple plane is the column space of matrix A, where vector v1 is a vector from the first column, the vector 0, 1, 2, and vector v2 is a vector from the second column, the vector 1, 1, 1. The red point is the terminal point of vector b, the vector 6, 0, 0, and the blue point is a terminal point of the vector resulting from matrix A times the vector x hat, which is the vector 5, 2, 1. We can also say the vector 5, 2, 1, where the vector resulting from matrix A times vector x hat is equal to vector b projected onto the column space of matrix A. And again, the distance from the vector 5, 2, 1 and the vector b is equal to this distance here, the square root of 6. So again, the least square solution minimizes the distance from matrix A times vector x hat to vector b. And the components of vector b minus matrix A times vector x hat is equal to vector b minus the projection of vector b onto the column space of matrix A, which is also equal to the projection of vector b onto the orthogonal complement of the column space of matrix A. I hope you found this helpful.